This is part 1 of lecture 4.2 equivalence relations. In this video, we will give the definition of an equivalence relation and learn how to obtain the equivalence classes under that relation. Let A be a non-empty set. An equivalence relation on A is a relation on A which is reflexive on A, symmetric, and transitive. The definitions of each of these properties is given in part 4 of lecture 4.1. If the object A is related to the object B under an equivalence relation R, we sometimes say that A is equivalent to B. There are two sets that we associate with an equivalence relation on A. First is the equivalence class of any object small a in A. This is the set of all elements B in A such that B is related to A. In other words, the equivalence class of small a is the set of all elements which are equivalent to A. Second is the collection of all equivalence classes in the set A, which we sometimes call A modulo R. Observe that since R is reflexive on A, each object in A is an element of its own equivalence class. Consider the identity relation on a non-empty set A. For any element small a, the equivalence class of A is the singleton with element A. Hence, the set A modulo the identity relation is the set of all one-element subsets of A. Consider the relation A cross A on a non-empty set A. It can be shown that this is an equivalence relation on A. Since every element small a is related to every other element of the set A, the equivalence class of small a is the entire set A. Hence, A modulo R contains only the set A. For a fixed positive integer m, consider the relation congruence modulo m. Recall from lecture 4.1 that the integer a is congruent to the integer b modulo m if and only if m divides a minus b. For any integer a, the equivalence class of A is the set of all integers B such that B is congruent to A modulo M. That is, M divides B minus A. By the definition of divides, for some integer k, B minus A is equal to M times k. Equivalently, B is equal to mk plus A. So the equivalence class of A is the set of all integers of the form mk plus A for any integer k. By the division algorithm, there exist unique integers q and r such that A is equal to mq plus r and r is greater than or equal to 0 and less than or equal to m minus 1. We will show that the equivalence class of A is equal to the equivalence class of the remainder R. Indeed, for any integer k, mk plus A can be written as mk plus mq plus r, which is equal to m times k plus q plus r, which is an element of the equivalence class of R. This shows that the equivalence class of A is a subset of the equivalence class of R. Note that this, together with the division algorithm, implies that every integer in the equivalence class of A also has remainder R when divided by M. Now, mk plus r can be written as mk plus A minus mq, which is equal to m times k minus q plus A, which is an element of the equivalence class of A. This shows that the equivalence class of R is a subset of the equivalence class of A. It follows that the equivalence class of A is indeed equal to the equivalence class of R, where R is the unique remainder when A is divided by M. This gives us an alternative definition for the relation congruence modulo M. Two integers A and B are congruent modulo M if and only if they have the same remainder when divided by M. Thus, A modulo R consists of all equivalence classes of the integers R from 0 to M minus 1. A common symbol for A modulo R is Z subscript M. You will study this set again in your future math courses. You have come to the end of part 1 of lecture 4.2. Before you proceed to part 2, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.